Last time I saw you guys, we started talking about exponential growth, right? So we started comparing linear growth or constant addition or subtraction, okay? And then we talked about comparing it to exponential growth, which is constant repeated multiplication. So they're very similar in that they have a starting value and then they have something going on over and over again. The only difference is that we have added or subtraction repeated, or we have multiplication or division repeated. That's really the only difference here. And we went through 4 different examples for 4 different patterns, A, B, C, and D last time I saw you. You guys worked with the same ones in your homework assignment, okay? So A, B, C, and D, we had 2 linear and we had 2 exponential. And we can tell by looking at these shapes that there is a big difference. These guys are going slow in their growth, kind of like stairs. They're just constant. Versus exponential, it's kind of hard to see in this one, but this one especially, we can see it starts out tiny and it gets really big really fast. And if you remember, this one was a tripling rule. It's getting multiplied by 3 repeatedly. So just think how big the next one, section 5, would be if we continued this pattern. This was 81. So the next one would be 81 tripled. It would go off the paper. It would be way too tall. We wouldn't be able to see it. So that's the thing with exponential growth. We're multiplying. Things are getting bigger more and more and more quickly, okay? So today we're going to talk about writing the equations for these patterns or these rules. And linear growth we should be pretty comfortable with. That's what we've been talking about all year, okay? So we have our formula for our function for a linear function, mx plus b, okay? And the first thing that I want to talk about is which parameter. Parameter is just a fancy word for something that we call a variable, but then we end up putting a number in it. So m and b would be our case here. X and f of x stay as those letters, okay? We want to know which one represents the initial value. Well, if you think about lines, right? M and B are 2 things, okay? M and B are 2 things that determine the shape of the line, how it grows, which direction it grows in, okay? The initial value is where that graph starts, as I would say in class, right? Starts. And it starts on the y-axis or on the y-intercept. So B is the initial value because it's when x is 0. Okay, when we're talking about initial values, it's always step 0. Okay, so in our first example here, this was a linear growth because we were adding repeatedly. Step 0 would be our initial value. In this case, it was 1. We determined those numbers last time I saw you guys. Which parameter is the rate of change? Well, rate of change is just a fancy word for slope. So m is going to be the rate of change. Okay, m's our rate of change, and that's because it's our common growth. Okay, or slope. Slope, rate of change, same thing. Okay, and in this first example, we were adding 2 for every 1. So my slope here would be the change in y over the change in x, or 2. Okay, if this was going up by 2's, we might have a different situation, but in this case, we're going up by 1's. So change in y over change in x is our 2. Okay, that should be something we're pretty comfortable with here. Okay, now we're going to go to the exponential, and it's similar, but it's also very different. Okay, so we use a and b when we're talking about exponentials, and this guy right here is our formula that we use. Just like y equals mx plus b, or f of x equals mx plus b, we now have f of x equals a b to the x. Okay, so which of these represents the initial value or the starting value? So remember, again, this is when x is 0. Okay, this is our y-intercept still. Our initial value is our y-intercept still. But in this case, when we graph this thing, it's not going to be a line. It's going to be curvy, and it's going to get really big really fast. So in this formula, the initial value is going to be a. Okay, and the reason being is if we raise b to the 0, that's just 1. Okay, anything raised to the 0 power, and you could check this in your calculator, any number that you raise to the 0 equals 1. Okay, so what this turns into is a times 1, or a. So a is always going to be our initial value, okay, which leaves one other letter for the second question, the growth factor. That has to be b. Okay, and the reason that b is our growth factor is because we are raising b to a power. Okay, when we raise b to an exponent, that means that b is getting multiplied over and over and over again. The x right here is attached directly to the b. So if we want to find the second step, we would have a 2 as the x, because that would be our second step in our series, okay? We would raise b squared to have that 2 as a factor twice, okay? Now, let's come up with our explicit rules or our functions or our equations for our 4 patterns. So we already started on pattern A, okay? So A was a linear growth, as we remember from last time I saw you guys, okay? Section 0 is 1. Guys with the chat, please, if we're just fooling around, I'm not going to be happy, okay? Section 0, we have 1 to start. So that means that our B value is 1, because that's where we started when x was 0, okay? And our m, our constant growth, our constant rate of change was 2 per 1, or just 2. So that means our slope is going to be 2. So my function for pattern A will be f of x equals mx plus b, okay? So we've got our explicit rule for this linear growth, and I'm going to put an L so we remember that it's linear, because linear means addition, okay? And we can tell because we have a plus sign. Plus sign means addition. We go back to our pattern B from last class, guys, and we've got this exponential growth. We figured that out because we were multiplying by 2. We were doubling for each step along our pattern. Our initial, right here, we can see step 0 was 3, or we can recount it from our picture, okay? So that means that my initial value is 0. A, if you remember back up here, is also what represents our initial. So our A value for this function is going to be, 3. 3 in that first step of the pattern. Now we need our common number that we're multiplying by. Looking at our numbers, 3, 6, 12, 24, 48. Every single time they're growing by doubling. And we determined that last class, so that means that my B value, or my repeated multiple, is going to be 2, because doubling means times 2. I have A, I have B, I plug it into my function. F of x equals A times B to the x. Look kind of similar. They have an x somewhere in there. Their operation is drawn very clearly. We have a plus sign and a multiple. Okay, so we've got our exponential growth for pattern B. We got 2 more going on here, guys. Okay, pattern C was another linear growth. We saw it last time that we were adding 4 repeatedly, starting at 1 from our recursive rule. So since we were starting at 1, my initial value B was 1. My repeated addend was a 4. So now I have both my numbers for this linear growth model. F of x equals mx plus b. And again, these guys are review. Okay, we've been talking about lines for lots and lots of time here. Okay, last example is one more example with exponential growth. Okay, so looking at this guy, we determined these patterns last time. We started with 1 in section 0, and every single time we were tripling. So we became 3, then 9, then 27, then 81. We could keep going forever. Starting at 1 means my initial value called A is going to be 1. Multiplying by 3 or tripling every single time is going to mean that B equals 3. So my function here, f of x, is going to equal A times B to the x. And again, one more example of an exponential function. Okay, so they are very similar. Linear functions and exponential functions are very similar. We just change the operation in the place that the x is. Okay, let me